My dear students, very good morning and welcome to this series lecture session on EC402 Nanoelectronics of 8th semester Electronics and Communication Engineering program of KTU. Today, we are going to discuss about the perpendicular transport of electrons in quantum nanostructures under the influence of electric field. What is perpendicular transport of electrons? What are the effects of electric field upon the perpendicular transport of electrons? In perpendicular transport of electrons, that is, motion of carriers occur in a direction perpendicular to the plane of the potential barrier separating the quantum structures. Perpendicular transport is often associated to quantum transmission or tunneling because the carriers do not need to have enough energy to surmount the barriers. When a particle goes through a potential barrier, the wave functions and its derivative in the perpendicular direction must be continuous, which leads to transmitted and reflected wave functions. The tunneling effect through potential barrier leads to the negative differential resistance in the IV characteristic of the device. The resonant tunneling through a potential double barrier is one of the quantum vertical transport effects in the nanostructures. Now let us consider what is meant by resonant tunneling effect in semiconductors. We know that the electrons in the quantum wells or heterojunctions can attain high mobility under the influence of an applied electric field parallel to the interfaces. But if the applied electric field is perpendicular to the potential barrier at the interfaces, electrons can tunnel through these potential barriers, constituting a perpendicular transport of electrons. The tunneling rate through two thin potential walls, which form a quantum well, increases enormously if the incoming electron has an energy coinciding with one of the allowed energy levels in the well. That is, the electrons can tunnel through both walls if its energy corresponds to one of the allowed energy eigenvalues within the well. This phenomenon is called the resonant tunneling effect. The tunneling currents through heterostructures can exhibit zones of negative differential resistance, which arises when current level increases for increasing voltage. Now we will see the resonant tunneling effect of a double barrier nanostructure under the influence of an electric field. Figure A shows the energy band diagram of a double barrier nanostructure made of undoped gallium arsenide surrounded by aluminum gallium arsenide on each side. Figure B and C shows the same structure under the increasing applied voltages. That is, we apply an electric field to the quantum well of the nanostructure. See, figure A is this one. Here, the double barrier nanostructure has a quantum well formed here. E1 is the quantized energy level and EF is the Fermi level energy. And this structure is now not applied with an electrical voltage, or there is no field applied on figure A. This is the structure. Now, if the same structure is applied with an electrical voltage, so that an electrical field is applied here, so what happens? When the incident energy E becomes almost equal to the quantized energy level E1 of the well, resonant tunneling occurs in the well. For a voltage, V1 is equal to 2E by E, where the incident energy E coincides with E1. So, the voltage V1 is equal to 2E1 by E. Let us see the case here. See, When the incident energy E coincides with E1, then resonant tunneling occurs in this quantum well. So under the resonant tunneling condition, if the applied voltage is increased, that is the electric field is increased, and the voltage reaches to a value 2E1 by E, then at that particular condition, what happens to the well? At that particular condition, the Fermi level EF of the metallic contact on the left side coincides with the N is equal to 1 level in the quantum well. At that condition, the tunneling transmission coefficient in the quantum well approaches unity and a large current flows through the structure and reaches to a peak current for the applied voltage V1 is equal to 2E1 by E. See here, when the voltage is increased and the incident energy increases and incident energy is impinging on this one and impinging on the barriers, that is tunneling barriers here. When the resonant tunneling occurs, then applied incident energy will be almost equal to the quantized energy level. At that condition, that particular condition, the resonant tunneling occurs here and the voltage increases to a value 2E1 by E. And at that particular condition, that the transmission coefficient of that particular quantum well will be almost unity. It means that the current in the quantum well will be increasing pretty steeply like this. It increases like this and reaches to a value. Usually we call it as the peak value of current at a voltage 2E1 by E. So when voltage V is equal to 2E1 by E, the current will become the peak value. And if the voltage is further increased, what happens? If the voltage is further increased, that is, it is more than 2E1 by E, then the Fermi level energy EF surpasses E1 and the current through the structure decreases. See, that is shown by the IV characteristic here. After this voltage V is equal to E1 by E, if we increase the voltage further, then the current decreases, showing the IV characteristic with a negative voltage region or a negative slope. So this is the IV characteristic region where the negative differential resistance region comes, or the slope of the IV characteristic becomes negative. Now this continues till a voltage VV is applied on the quantum well, and this voltage VV is the value of the current, which is the valley current. So the current reaches to a valley current IV to a voltage VV applied across the junction. So on this junction, on this quantum well, on this resonant quantum well, the applied voltage reaches to a valley voltage VV, the current will be IV. After that particular value of voltage, if we increase the applied electric field further, then the current in the quantum well increases like this. So this is the nature of the characteristic feature of the quantum well under resonant tunneling conditions, and this is the IV characteristic of the quantum well under resonant tunneling. Now we have to see the transport of, that is, perpendicular transport of electrons through the quantum well under resonant tunneling condition depends mainly upon the transmission probability coefficient of the barrier. The transmission probability coefficient means that that is actually the transmission probability coefficient that actually determines how much electrons will be transported through the potential barrier, or which is penetrated through the potential barrier. So in order to understand the transmission property of the resonant double barrier, let us consider the transmission probability coefficient of a single barrier, which continually increases with energy E of the incident electron if the ratio of the incident energy E by the electron charge is less than the applied voltage, say V0. Now, for the double barrier structure under resonant tunneling condition, The transmission coefficient is given by the product of the transmission coefficient of barrier 1 and the transmission coefficient of barrier 2. If T is the transmission coefficient of barrier 1 and Tc is the transmission coefficient of the barrier 2, then the transmission coefficient of the double structure under resonant tunneling will be given by the product of T and Tc. Now, if the two potential barriers are identical in nature, then the transmission coefficient will be given by the equation T is equal to T0 square divided by T0 square plus 4R0 cos square Ka minus theta, where T0 and R0 are the transmission and the reflection coefficients of the barrier, and A is the well thickness and K the electron wave number of the wave function of the wave, and theta is the phase angle. To understand the difference of the transmission coefficient on the incident energy E, now let us consider an electron energy impinging on a resonant double barrier structure shown here. See, this is a double barrier structure under resonant tunneling condition, and this is the incident energy E. And this incident energy, the quantized level of energy E1, E2 and E3 are here is the quantum well for which is having these three levels of energy E1, E2 and E3. And figure B shows the variation of transmission coefficient with the incident energy, with the increase of incident energy. So, figure B shows the difference of transmission coefficient T as a function of the incident energy E for the resonant tunneling nanostructure with the three energy levels in the quantum well, that is E1, E2 and E3. Now, let us see the conditions here. If you consider the resonant tunneling occurring on each levels of energy E1, E2 and E3, see the transmission coefficient at E1 will be approximately equal to 1. Again, the transmission probability coefficient or transmission coefficient of E2, the E2 energy level E2 will be 1. And again, transmission coefficient of E3, transmission coefficient of the resonant tunneling during the resonant tunneling at the quantum well will be equal to 1 at E3. So, at each energy level, the transmission coefficient equals to 1. But here, we can see at each resonant peaks occurs during the resonant tunneling conditions. We can see that at each energy level, the width of the tunneling peaks will be different. Or for E1, this is the width of the tunneling peaks. And when the energy increases to E2, or at higher levels of energy, the resonant tunneling peaks increases. Again, for the energy level E3, again the resonant tunneling increases, or the width of the resonant tunneling increases, or is widened. So it means that the resonant tunneling peaks increases, or the width of the resonant tunneling peaks increases with the energy levels. Why is it so? So the reason for this can be very easily available with the explanation of Heisenberg uncertainty principle. The difference of energy levels, that is E2 minus E1, that is given by delta E, should be inversely proportional to the lifetime tau of the state of electrons in the quantum well. What does it mean? It means that the electrons at higher energy levels in the well have to tunnel through lower effective barriers and should therefore have a shorter lifetime tau. It means that at higher levels, the electron has to penetrate or tunnel through the lower effective barriers of the quantum well under resonant tunneling. And the electrons there will be having or the electrons in the quantum well at that particular time will be having shorter lifetime tau. So with this, we conclude this session here. The next class we will be discussing about the effect of electric field on superlattices. Thank you.